Uh, so thank you for the organizers for giving me this chance to represent my talk. I mean, my work with Pasha on this topic, and also thank everybody who came to this virtual meeting to, uh, yeah, who are interested in my work. Um, so today's topic, as mentioned in the abstract, is the Robinson-Schensted correspondence for natural unit-interval orders. Yeah, Robinson-Schensted. I mean, so I need to define what the Robinson-Schensted correspondence is and what natural unit-interval orders is. I need to define two notions. And this work is joint with Pavlo Pylyavskyy, who's in the chat room as well. Okay, let's start. So I first define what the title means, and I will say about the motivation, and we will define some notion of P-Knuth equivalence. Here, P is the natural unit interval order, which I will define in a moment. And then we will talk about the letters, which is some kind of special kind of natural unit interval orders. And then we will prove the main theorem. And to prove the main theorem, our main tool, which is equivalently important as the statement of the main theorem, is this Robinson-Schensted algorithm for P version. So we will discuss this in detail, but if I have time, or I mean, I can just skip it if it is too complicated, but yeah, we'll see. So let's start. So the Robinson-Schensted correspondence usually is the bijection between n-valued matrices. So it's a matrix with, elements in the natural numbers. Here, well, you see that I used a convention that 0 is a natural number as from Pn axiom or ZFC axiom. Well, I prefer to have 0 in the set of natural numbers. So this one has no contradiction. And it maps to the pair of semi-standard Young tablet of the same shape. And this lambda is a partition whose size is equal to the sum of all entries in this n-valued matrices, right? And it is usually described in terms of bumping process. So you can, for example, you can just look at the paper, this like fundamental celebrated book of Richard Stanley, and enumerate combinatorics chapter 7. Then there is a process which describes this process really well. And if you restrict your attention to Sn, which is, here we identify Sn with a set of permutation matrices. So you have you have zeros everywhere, except you have 1 on each row and each column. So it's like a non-attacking rooks. And they map to this pair of standard Young tablet in this case, and it is still a bijection. And this is called usually Robinson-Schensted correspondence. The Knuth version is the generalization of this picture to here. So I'll give you one example about the RSK correspondence, Knuth version, but you see how it be restricted to the Robinson-Schensted original version. So suppose that you have a tablet here, and you have 1 to insert. Then what you do is to find the number on the first row, which is bigger than the input, but on the leftmost one among them. So this is 2 in this case. You bump it, and then so you replace this 2 with 1, and then you see that this 2 is bumped out. Now you look at the second row and see, well, 3 is the number you need to bump. So you do the same thing. Well, here is 4. And finally, you have 4, and here 4 is not small, not bigger, so you cannot bump 4 here. But here, our convention is that we kind of assume that infinity is everywhere outside this tableau. It's like like you can assume that this is a shore. This is the ocean of infinity. So you can bump infinity in this case, and you will have this picture. But this is the RSK correspondence, and if you restrict that to standard Young tableau, then you will get the Robinson-Schensted version. The other thing is that we need to define natural unit interval orders. So here, for the sake of simplicity, we assume that we have a partial order which satisfies that if A is greater than B respect to this order, then A is greater than B respect to the usual order. Okay, so this symbol is for the usual linear order on the set of numbers from 1 to the n. And here, this symbol is for, for the partial order that we will discuss. And we write A, right arrow sub P, B, if A is bigger than B respect to P. Here, so our convention here is motivated from the fact that this arrow, the head of the arrow, looks like the inequality. So that is the reason I chose this. And well, it is usually different, the opposite from the usual Hasse diagram, but I prefer this notion. So, well, or you may just think about this like, going down process, like this GKM basis, like, from top to bottom by just differentiating, something like that. And we say A dash B if A and B are not comparable with respect to P, okay? And A dash arrow B if they are not comparable in P, but they are comparable in the usual order, which is definitely possible, and this A is greater than B, okay? So this arrow will be decomposed into two pieces where the bar part is kind of like comparability of this partial order, and this head of the arrow is basically this one, the usual one. So we do not need something like this one, because if this is true, then it means that A and B are comparable with respect to the usual order, and then this, they are comparable with respect to P. So this is, well, just a combination of A, B comparable, and A is greater. I claim that this is equivalent to saying that this because of our linearization assumption. So that is the reason I use this symbol instead of this one. Then the definition. We say that P is a natural unit interval order if for any number ABC such that A is greater than C with respect to P, A and B are not comparable, B and C are not comparable, we have A, B, C in this order respectively. So it means that if you have A, C, B, and you have this, and this, and the order, the usual order will give you this rank, say. And then this B here cannot be bigger or smaller than this interval. So another way to describe this natural interval order in more detail or more intuitively is to introduce this diagram, interval diagram here. If P is a natural unit interval order on these numbers, then there exists these numbers, real numbers, y1 to yn, such that they are in this increasing order, which is which gives you the fact that our order is respects the usual order, and A is greater than B if and only if YA is bigger than YB plus 1. So here, you may see that in this diagram, the starting point of each interval will be y1 to y6. And you see that it is in increasing order. And here, if 1 is not smaller than 2 with respect to p, because, I mean, this part, the endpoint is not, I mean, not smaller than the starting point of 2. So it means you shouldn't have overlap to compare two elements in P. And then you see why it is named natural unit interval orders, because, you know, these starting points are in the natural order, so it's a natural, and then you have unit intervals, so it's a unit interval order. Okay. So here, well, 1 is smaller than 3, 4, 5, 6, but not 2. So that is the reason you have these arrows, and well, 6 is smaller. Yeah. And here, for 2, same thing happens. For 3, the only thing which is bigger than that is 6. So you have only one arrow from here. Same for 4. 5 is not comparable to 6, so you do not have arrows between them.
There is a question.
Yep.
It's in the chat.
Oh yeah, can you please show the restriction on the previous slide? Which restriction here?
Yeah, the one below on the right. Thank you. Thank you.
This one? You should show the restriction. Oh, will you please elaborate? I mean, what does that mean? Yeah. Okay. Now, the third definition is equivalent extra as well.
Excuse me.
Yeah.
Can I have a question about the previous slide?
Yeah.
So about what is the length of these intervals, like interval 1, 2, 3, 4, 5, 6?
It is usually 1 as described here, but I mean, actually it doesn't matter because you can just define, you know, this thing using, I mean, you know, by just choosing these numbers and choosing the interval, the length of the interval for each one. It doesn't matter, but well, I mean, conventionally we say the length of the interval is 1 because, I mean, this is natural unit order.
I see. Oh, so it's a closed interval. So that means that if I see.
Yeah, I mean, it doesn't matter if.
Then I see. Okay, got it.
Yeah. They have to be the same. They have to be the same length. Otherwise, it's not equivalent to your previous definition, right?
It's true. Yeah, I believe so. Yeah, they should be all. Yeah, you're right. I mean, they should be all equal length. Thank you. Right. Yeah, Sam, I mean, clarified that like it is different in general. Now the third condition, the equivalent condition, is that P is a natural unit of order, then there exists a partition. So we will have this partition, which is in this case 3, 1. That is my convention. Then you can choose different convention if you want, such that A is smaller than B. If and only if A is smaller than this number. But I mean, what I mean here is that 1 is smaller than 4 if you have these arrows in this partition. So if you can draw these arrows in this partition, so there are 4 arrows here, then they really give you the correct natural unit of order. And in this case, we write this way. So in general, there is a one-to-one correspondence between this natural unit of order and the partition in this, you know, staircase. So you see that the number of the natural unit interval order on 1 to the n is given by some value which lets you enter this channel, right? All right, so now let's talk about some motivation. So recall the fundamental of quadrisymmetric function. Well, it is, you know, if you have, well, this one, and well, you have subset of, it should be, sorry, it should be, yes, I should correct it. if it have a subset of this interval 1 to n minus 1, then it gives you some part where your index should jump. So this is just a sum of all these monomials where the jumping happens, jumping happens in this set of numbers which you pre-designed. You can jump elsewhere, it's okay, but if you have, oh wait, I think you can. Oh, it should be not. It shouldn't be event only. Sorry. I think this is the action. Is it? Yeah, I think so. So in that case, you have some monomials, and you see that this is a quadrisymmetric function, which is not a symmetric function. So something similar is bigger than the set of quadrisymmetric function is bigger than the set of symmetric functions. You have some kind of symmetry on this quasi part. For W in Sn, we define its p descent to be this way. So here, well, you have it's kind of like genuine p descent. I mean, I want that this number is greater than this one. It's a usual descent, but I want these to be, comparable in p as well. So that it's kind of really descent in p as well. So it's a genuine version. And I want this quadrisymmetric function, the sum of this fundamental quadrisymmetric function where you sum over all these elements in Sn. And this one is basically, you give, for each W, you have a set, which is a subset of this 1 to n minus 1. So you can define the quadrisymmetric function corresponding to it. And you take the sum. I would say that this is some kind of generating function for P and the set Sn. And if P is a usual order, then you can easily see that this is just the usual homogeneous symmetric function. So what is easy to prove is that this is a symmetric function and P positive. A little technical, actually very technical, is that this function is Schur positive. So this is a character of some real representation of Sn. Conjecture.
Sorry, what is P positive and Schur positive?
Oh, Schur positive? So
And P positive, yeah.
Yeah, so function is Schur positive when it is a positive non-negative sum of Schur functions. So it can be written as the S1 plus, say S2 plus S11. You may take 3, and it's Schur positive. It can have 0 here, doesn't matter, but you cannot have minus value. And well, yeah, maybe it's more stronger than that. Actually, these numbers are all natural numbers, so it's not just Schur positivity for real numbers. Right. Conjecture, which seems to be really hard. Nobody knows how to prove it in general, I believe. If someone already proved it, please write it, your draft and then show it to me, or put it on archive so that I can be satisfied. Probably, I can upload the slide. Yeah, doesn't matter. Yeah. The conjecture is, this is H positive. So it is some natural number combination of the complete homogeneous symmetric functions. There are some partial progress. Well, a lot of people already have done some partial, progress on this conjecture. And well, in general, it's not known. And well, I believe that it's kind of the most fascinating, interesting conjecture in algebraic combinatorics, because the statement is really simple. Well, this is H positive or not, and it has a lot of interaction. Say it is related to Hessenberg variety, it is related to GKM theory, it is related to, well, in our case, it's related to graph theory as well. But I mean, it's really hard to understand why this should be true. Maybe, I mean, there can be some kind of heuristic reason why it should be true, but at least for me, well, I still don't know whether it should be true or not. It is too good to be true. Well, if it is a theorem, then I would be really happy. If it is not true, I wouldn't be surprised actually. But still, I mean, it's a beautiful conjecture. I want to know something at least.
Do you know for which n it is known to be true?
I don't know. I mean, it really depends on which supercomputer are you using, I think. Well, I calculated up to n equals 12 or something. That is true. Well, I mean, I believe that there is some kind of a joke in Russian Russian mathematics that if it's true up to n equals 9 is true. I don't know. But I really don't know. I mean, I really want to calculate this on some supercomputers so that the validity is, or we can have more examples how this H function will look like.
Yeah, I think Alejandro has a supercomputer. He says it's 20 plus.
20? Wow. Great. It's true. Oh. I don't know.
So I have a quick question. So is the conjecture for the original conjecture is for interval orders, right? And you're looking at
yes
orders here.
Yeah, actually
between the two of them or something.
Yeah. So the actual conjecture was actually for this chromatic symmetric function on the graph where you avoid some pattern. So it is you avoid 3-1 pattern, I guess. But it is reduced to this situation. So actually, I mean, for interval, so if you remove this natural part, it's kind of equivalent, but you kind of add, it is proved that you can only discuss the orders for 3-1 avoiding and 2-2 avoiding as well. So this 2-2 avoiding part is added later, and it is equivalent to actually the interval orders.
Thanks.
And now you have a graded version. So for this W, we set this fake P inversion to be this way. So, for the usual inversion, you have two numbers, and it doesn't need to be adjacent. And this one is bigger than this one, so it's called inversion. Here we do something more than that. Here we compare Wi and Wj. It is in reverse order, with respect to the usual order, but I want these two to be not comparable in respect to P. So that is the reason it's called fake P inversion. Okay. So if you have a usual order, then there's no fake inversion. If you have a trivial order, then fake P inversion is the same as the usual inversion. But here it is something in between. Now we consider the following weighted version. Here you have this weight kept by the power of P. So it's a number of fake P inversions. Okay. Then the theorem of Schur and Wash is that this is also a symmetric function. Well, so it's that each coefficient of T, the monomial of T is, each coefficient of Tn or Tp or whatever, it is a symmetric function, and both P and Schur positive. So it's kind of stronger because you split this, usual generating function into pieces by the gradient. Now the conjecture is that this is H positive. Well, it is also not known. It's a stronger conjecture. If Stanley-Stembridge conjecture is true, then I wouldn't be surprised that this graded conjecture is also true, but I don't know. I really don't know. Now let's go to Hessenberg varieties, which is a little, you see it's a little outside of algebraic combinatorics, but it's closely related to the Stanley-Stembridge conjecture. So for this partition and the regular semi-simple element, so you may consider a diagonal matrix with different eigenvalues. then we define the Hessenberg variety corresponding to lambda and S to be the set of flags where S, if you map Fi under S, then you will get this quantity, this contained is a subspace of this one. So it depends on the this partition here. That is our actually motivation why we use this convention to enumerate this naturally negative orders. So here we claim that the F in this diagram F1, if you map it, S times F1 should be contained in S4, I think S3, S3, sorry. And then S times F2 is contained in F4, S times F3 is contained in F4, and there's no restriction on F4 and so on. So you see that if you have a full, partition in your staircase, then it is the usual Springer fiber. If you have a trivial partition, then it is a whole flag variety. So it is also something in between. And also this variety is smooth. So it is really a good variety actually. Timosco defines this dot action on this one using this GKM theory. Well, yeah, and you have a moment graph. So it is, again, a graded SM module where I will not discuss how it's defined in detail, but, well, you can define this using GKM theory, actually. Then the theorem of Brosnan and Chow and Kipake is that the Frobenius character, if you just take, take the character of these module and then you take the graded sum, then it is really equal to our generating function. It's kind of surprising. Right? So that is probably the reason why this is really, one of the reasons why this is really interesting. Here, you want that each piece of Hessenberg variety gives you some permutation character of the symmetric function. Well, I'm not sure whether it's true or not. It really doesn't seem like it. But the hope is that maybe you can find some kind of good basis which gives you the permutation representation of this one using, I don't know, maybe canonical basis. I'm not sure. But yeah, there are also some progress recently. How to choose a good basis is at least for the toric variety case. Now, our goal is to understand combinatorics behind the picture. So I want to introduce P-Knuth equivalence, which is the P version, and define the P Robinson-Schensted algorithm, which is also the P version, and use this combinatorial tool to analyze this function in detail. So we are not going to prove the Stanley-Stembridge conjecture, but still, we will do something to understand this in more detail. Now, we'll talk about P-Knuth equivalence. So usually, the Knuth equivalence gives you this. So it's a right-star operation. You have 3 numbers in some string, and suppose that A, B, C are in this order, and you have descent here. Then there's no descent here, right? Then there is a way to move this descent to the next and remove the descent here. So it's like moving descent 1 by 1. Here, the thing is that you just fix the middle number and switch the numbers in the farther away. So like A, you switch A and C. Same thing happens, you have B here, so you switch C and A. In this case, the descent is moved from here to here, and vice versa. So this move is called Knuth move, and it is some kind of equivalence. It gives you, how can I say this? You can consider the equivalence relation generated by these moves and there is it is called a P-Knuth equivalence classes in the set of words or set of strings. So, and then this is basically the definition of the flat monoid. Now, for each equivalence class gamma, consider the following generating function here. So you just restrict your attention to gamma. Here, it is a usual descent, which means that we are talking about the usual order, not just the arbitrary naturally into order. Then, surprisingly, I mean, this is why it's like trivial. Well, I mean, it means that Sn is decomposed into equivalence classes. It's a set theory exercise. But the surprising thing is that each function is actually a Schur function, not only Schur positive, it's really just a single Schur function. So this is the decomposition of S4 into Knuth equivalence classes. You see that each part gives you exactly one Schur function. And this bar will be, it gives you where the descents are. So you have the two bars here, it means that you have these two descents, and here and here. Now I will define the P version of Knuth moves and equivalence classes. So we have these 4 possibilities where we have the P Knuth equivalence classes. There's one thing we miss in this diagram where A, B, and C are not comparable pairwise. And in that case, there's no P Knuth equivalence class, so we don't need to worry about it. Whenever we have some comparison between some numbers, I mean, these are the only possibilities. And in that case, we will define this P Knuth equivalence class like this. So, well, firstly, you see that these numbers have like different descent for each line. So it is, well, kind of has the spirit of Knuth equivalence Knuth moves. But one thing which is a little different, sorry, from this is that, especially this part. So here, usually the Knuth equivalence just moves the two adjacent numbers. So, and then you just have an observer in between. But in this case, B and CA are swapped, like a rotation. You may say that it's a rotation or like a swapping. So it is one tricky thing you need to worry about. But otherwise, well, the other things are similar, more or less, even if sometimes you just fix C and swap AB instead of fixing B. But there are two versions, two moves where you may either fix B or fix C. Here you fix A or fix B, and in the usual case, you have the usual Knuth moves. And then you can also define the equivalence class. So these are the rules that we implemented for this P. I mean, the naturally into order. Well, it is not clear at this moment why we need to define this way. I may say that it is more or less the only way to make this theory work and efficient. Well, you can put more equivalence, more moves, then the result can be a little coarser. And if you take out some moves from here, then it wouldn't give you pure positivity. And if you change these rules, well, I believe that it's not like comparable as you go up, as you increase the rank of the symmetric group. So I believe that this is the optimal version. Anyway, for example, so if you have trivial partial order, there's no Knuth move. If you have a order, you compare only 1 and 3 here, then you see that 3, 1, and 2 are swapped, and there's no Knuth move for the other things. And then you can see that you have 2 Knuth moves for the other naturally interval orders. Now, you can also define this generating function for each equivalence class. So that, I mean, the sum is basically the graded generating function which appears in the graded Stanley-Stembridge conjecture. Well, the question, as before, is that if this one is a symmetric function, it's not clear yet. Well, if it is symmetric function, it is true positive. It's not clear, definitely. Another question, if it is a Schur positive, then is it single Schur function? Well, if it's a usual order, then the answer is yes. But in our case, well, we'll see. So this is the example when you have this order. So it is 1, 2, 3, 4. 1 and 3 are comparable. 4 and 2 are comparable. 4 and 1 are comparable. But I believe that that's it. Other things are not comparable. In this case, you can just decompose this into these pieces. But you can easily see that this one is not a single Schur function anymore. So the third question is definitely false. But at least you see that they are all Schur positive, right? It's fancy. So, oh yeah, I should have mentioned that this part, well, I mean, at first we do not know that this one is a constant on each equivalence class, but it's an easy combinatorial exercise that it is this value, the number of fake P inversions is preserved in this each equivalence class. So you may just like take it out and you can just consider the ungraded version instead. And the conjecture is that each generating function, this ungraded version, is a true positive symmetric function. And it's definitely a refinement of the theorem of Schur and Wash. It's still a conjecture. I don't know the answer yet. In full generality, I believe that this is true. I mean, it should be definitely true. But our proof relies on Knuth P Robinson-Schensted algorithm, where you need to avoid some kind of pattern. So that is the reason it's not proved in full generality. If you have any idea, please let me know. I'd be happy to hear that. But at least I will show you how how we approach this problem and try to solve this conjecture. Now, for example, these are the graphs of like for each Knuth equivalence class, and these bars are Knuth moves when these numbers are rare, this descents are moved, and different color means that if you just take out this red part, then it will give you, I believe that this is for S41. These 5 things is for F32. So these corresponds to each Schur function. You see that this part is kind of disconnected, right? It's not connected by the Knuth move, but it's connected by other series of Knuth moves. So I believe that it's in general impossible to just divide it into connected pieces and then say that each piece is a single Schur function. You need some kind of disconnected parts getting together to make a single Schur function. This is another example. You have S32 to S41. You see we have 3 colors here. Same thing happens here. You see that this is really farther from here, but I mean, I believe that this is the only way to make it work. Or, oh, actually, I can tell you later why I group these these elements in this way. This will be, spoiler alert, these colors are put so that each color maps the same P tableau under P Robinson-Schensted correspondence. And here, here. The problem appears here when you have this poset where you have 1, 2, 3, 4, 5, and what is this? 1, 3, 5, 4. I think this is this coset. In this case, well, I mean, it is still sum of Schur functions. It's Schur positive, but I have this, shaded part, which is supposed to be connected to these ones, but I put different color here for some reason, because in this case, our algorithm is not working. So that is the reason the pre-mentioned conjecture is still a conjecture. But I truly believe that this method should work in general. Like, I believe that the conjecture should be true. Right, now let's talk about letters and the main theorem. So we say that P is a letter. So a partial order is a letter if it is this one, which corresponds to the toric variety of the Hessenberg variety, for example. So you have, it's the chain of this interval. That is the reason I just named it a letter. It looks like a letter, right? Like, yeah. Or, well, if you put things like where numbers are not comparable, now it's more like a letter. And we say that it's a letter order. Sorry, this subset is a letter if the restriction of your natural interval order to this X is a letter order. Okay? So, for example, if the P is a letter order, then any connected interval is a letter. We say that someone is climbing a ladder. Okay. Someone is climbing a ladder. It's not just starting or ending, it's really climbing. It's in between the ladder, in the middle of the ladder. If, or P ladder climbing, if there exists these numbers such that this is a ladder and X is really between the starting point and end point. So, and we say that means in that case is a climbing a ladder, X is climbing a ladder, or, well, I mean, X is the climbing ladder, I mean, this ladder, I mean, this is also a ladder. And otherwise, we say that P avoids, P's not ladder climbing, or no one is climbing a ladder. Okay. So this is an example. This is two typical examples where you see someone is climbing a ladder. So here, 1, 2, 4, 5 is a ladder, and 3 is really climbing. It's bigger than 1, smaller than 5. So it's really climbing a ladder. It's in the ladder. It's not just the starting point, the end point. It's really in the ladder. This is another example. 1, 2, 4, 5, 6. And
Wait a minute. Do we have an arrow between 2 and 4 here?
No, shouldn't have.
And why do we have them interlapping on the right?
Here?
Why do we have them interlapping like 2 and 4?
Why do we have this one? Because, but there is.
Oh, yeah. Okay.
This is
sorry.
available. Yeah. Mm-hmm. And for this one, well, 1, 2, 4, 5, 6 is a letter, and 3 is in the letter. Or you may switch the row of 3 and 4. They are interchangeable. 3 is the part of the letter, and 4 is climbing a letter. You can say that as well. See, I mean, this is really a letter, someone is climbing. Actually, there's a theorem that P is not letter climbing if and only if P avoids these two patterns. So these are the only patterns which can appear when someone is climbing a ladder. If you avoid these two patterns, then, well, no one is climbing a ladder. Now, the main theorem is that suppose the P is a naturally interval order, which is not ladder climbing, so it avoids this 3, 1, 1 and 4, 2, 1, 1 pattern. And for any P Knuth equivalence class gamma, there exists a partition lambda 1 to lambda k such that this one is just the sum of Schur function corresponding to this lambda k. And well, this is the constant for each equivalence class, so you don't need to worry about it. And the length of these partitions are all equal. Well, if someone is climbing a ladder, then I still believe that the theorem is true, except the second part. There is a counterexample for the second part, but they don't need to be all equal length, but still, I believe that it's a sum of Schur functions. So if we go back to the these examples, and you see that these partitions are all the same length. Actually, it's kind of surprising to me. Let's see. And you have a, violation here. When someone is climbing a ladder, you have length 2, but here you have length 3. So it is a violation of the theorem. Still, I believe that the first part is true, but so so that is the reason I believe that avoiding a ladder is a natural thing to do, because, well, it is definitely simpler in a sense that you have more beautiful result inside avoiding ladder things. If you want to attack the things which climbs a ladder, then you kind of need to deal with this situation, and it will be a little more complicated. Okay. And for the proof of the main theorem, we need the Robinson-Schensted algorithm as P version. So it is equivalent. I believe that it's equivalently important for our purpose. First, we define the P tableau, which is originally defined by Gasharov. A tableau is said to be a P tableau if the entries of T are exactly one-to-n without repetition. Like a standard tableau. The entries are increasing on a column with respect to P, so each column is a chain, like standard tableau. The entries are non-decreasing along rows with respect to P, so they are not decreasing, like the standard tableau. So if P is a usual order and it's really a standard tableau, but if P is not the usual order, it's something different. It's a generalization. I believe that it's a correct generalization of the standard tableau for this P version. So suppose that we have this, this diagram, Hasse diagram, and this is, I believe that this is a P tableau where each column is a chain, and each row, if you look at 1, 4, 3, 2, from 1 to 4, it's not decreasing. 4 to 3, it looks like decreasing, but they are not comparable, so it's actually not decreasing with respect to P. 3 to 2, same thing. So 1, 4, 3, 2 is the sequence of non-decreasing numbers. Same thing happens for here. 5, 8, okay, increasing. 5, 8 to 7, not comparable. 7 to 6, not comparable. So it's a non-decreasing sequence. 9, they have only one number. So this is a P tableau. And the theorem is this. Suppose that P is not ladder climbing, and there exists a bijection, which is we call P Robinson-Schensted from Sn to the pair of tableau here. You see that the second part is still a symmetric Young tableau, but the first part is the P tableau instead of standard. So it's a generalization of standard Young tableau, but we need the same shape as well. And the first thing is that the descent of W is kind of preserved. You remember, if you have an original Robinson-Schensted, then it is also true. If you input this, you need to take the evacuation. It means that you need to flip it. Well, we kind of use the flipped version, so that's the reason. But still, descent is preserved in general. This evacuation means that you just take n minus x instead of just x. But it is also true for this P Robinson-Schensted. So this algorithm respects the descent. And W is the reading word of P. Should have mentioned what P is. P is actually this part, and Q is actually this part. So this one also respects the Knuth equivalence class. And the third part, C part, is basically, it gives you the same length condition, the second part of the main theorem. The partition will have the same length. So it's the length of the first column is equal for each equivalence class. And this is not true for ladder-climbing posets. But unlike the Robinson-Schensted algorithm, we do not have a single p-tableau for each equivalence class. For each equivalence class, you may need to attach several things, several p-tableaux. So that is the reason we do not have a single Schur function. But in general, it should be the sum of like Schur functions because you can attach p-tableaux. I mean, some p-tableaux, and they will give you the Schur function. So, wow, yeah, it's a little different. It's a little weaker than the usual Robinson-Schensted, but still it's really useful. But if you know this, how can I say this? If you know this theorem for P Robinson-Schensted, then you can easily prove that the main theorem, because, well, the second part is basically from C, and this one is, well, you may just use this one. So like, they correspond to the same reading word, and then you take this descent, and this is a bijection. So you kind of need to, for each p-tableau, you kind of need to enumerate all the possible symmetry Young tableau. And then if you collect the descent and take the fundamental quasi-symmetric function, it's known that it's a Schur function, but like the usual Robinson-Schensted. So that is the reason is true. Oh, I believe that I just didn't write down, well, how to define this Robinson-Schensted here. But it's a bit, I believe, yeah, we do not have much time, so I mean, I believe that it's actually nice. But yeah, I mean, let me just say briefly mention some couple of properties. So if P is the usual order, then it is actually the same as the Robinson-Schensted, but you kind of need to take the evacuation. So you kind of need to flip the words first so that it's really the same as the original convention. And the second thing is that in each process, you kind of have this, chain in each column. So it's more like a column insertion rather than row insertion. So you first have a word, and let me say it this way. So you first start with a word and you input it, and then you will make some column which is a chain, and there will be some shorter word, and then you start with this one, you put another chain, and then you will have shorter word, and you keep going, and then you will concatenate all of these chains and then get the p-tableau. So in this P Robinson-Schensted algorithm, it's kind of clear from the construction that each column is a chain with respect to P. The part which is not really clear is that the row is not increasing, not decreasing, and it is, well, I mean, because it's just a concatenation of chains. Well, we do not know whether this way is a non-decreasing one. If it is usual order, then it's kind of clear. But in general, you need to do some argument, and in our paper there is a really long, lengthy, complicated, nobody wants to look at proofs with really technical, I mean, it really just a case by case analysis, and we really need to rely heavily on the property that the poset is not ladder climbing. So it is used several times, and really it's a fundamental thing you need to use in order to prove this property. And in general, if you have this ladder climbing poset, for example, this one, then you really easily see that the result is not p tabular in general. So I believe that the one thing you'll get is that if you input 3, 2, 2, 5, 1, 4, it will give you, let's see, it'll be 3, 5, 3, 1, 4, 2. I think this is the answer for the usual the P Robinson-Schensted algorithm, but you see that 3 is greater than 1, so this row is not decreasing, even if each column is a chain. So there needs some modification for ladder climbing posets, but if you already avoided ladder climbing posets, then you're good to go. You can just use P Robinson-Schensted, and then you can just prove this main theorem. All right, so I think that's it. Thank you.